Hi, welcome to Lab 5 Ballistic Pendulum. This lab is pretty much the combination of all the previous 4 labs that we've done and to grasp a better understanding of momentum, Newton's second law, and the energy principle, and to understand the relationship between the height and velocity of the ballistic pendulum, and also predict the ball and calculate its velocity as it swings after colliding with another metal ball. And here are the physics principles we'll be dealing with: the momentum principle, Newton's second law, and the energy principle. And then what's given to us is a system of our project is the metal ball and the string. And the weight of the ball when neglecting the weight of the string is 12.3 grams and the drop height is 6.2 centimeters. So at that point, there will be a potential energy, a stored energy. And it is an inelastic collision, so the momentum is conserved, but kinetic energy is not conserved because initial velocity and the final velocity is not going to be equal. And we can see here in tracker that the ball is being hit by another metal ball, and as it's swinging, we can collect the information of its location, the X and the Y position. And with this, we can copy and paste it in the CSV file. So for the question, the string did not stretch at all, as you can see earlier, and also the speed and the tension of the string, we can calculate that from here. So we know the mass of the ball and its position, its initial position, and its initial velocity, we can find that. And also we know the measurements of the object, and it's 7 centimeters right here, 3 centimeters right here, and we can use tangent, arctangent, we can get the angle. So once we get the angle, we can use Newton's second law principle to find sum of the forces equals ma, and we can find the tension by this calculation, and the tension will be 0.06557 Newton for each side because there's 2 strings on the ball. So like we have mentioned earlier, the motion of the ball swings back and forth as it loses energy because the energy loss is detected by the sound of the 2 metals hitting each other. So the energy is converted to that sound energy. And then the ball eventually reaches equilibrium, or it becomes at rest. And it is similar to the spring because that's when there's force pulling the object or the spring back to its natural state or normal state or normal length. So the calculation we just showed, and there's no stretch in this case. And then the predicted speed of the ball, where is it at the max? So it's at the equilibrium state, which is when the ball is straight down, which is when the height is 0. So by the energy principle, the height is 0, so the potential energy is 0. So once the potential energy is 0, the kinetic energy is therefore at its maximum, making the velocity the max, because the potential energy is all converted to kinetic energy already. So we can see here the ball is swinging and its weight, the weight force is down and the tension is over here. So we break it down into 2 components, X and Y, or parallel and perpendicular. So when the ball is swinging this way, the weight force is pulling it down that way. And as the height increases, you see right here, the ball slows down and then it will come back to the right side. And so the weight force changes direction as the motion of the ball and its weights point in the same direction, the ball speeds up. So when it comes this way, it comes back down, then the ball speeds up because it's going the same direction. But the ball slows down when the directions are against each other. And when the ball comes back at rest, which is going to be right there, there's no net force. So the speed of the ball is at max right here because the height is 0, potential energy is 0. So what effect does it have, including damping or air resistance in our prediction? The air resistance slows the ball down, creating the percent difference in our prediction, the speed. And the ball eventually arrives at rest due to the energy loss of the system. Where did it go? The energy being converted to the sound we can hear the ball hitting each other. And just like I said earlier, the energy loss can be detected from the sound of the metal hitting each other, and the ball slows down and eventually come at rest. And this effect is similar to the result of air resistance. Creates slow down the ball. So after the ball makes contact, the system becomes inelastic, meaning kinetic energy or total energy is not conserved. Momentum is conserved though, because the external net force of the surrounding is 0. And we can calculate here, energy is potential energy plus kinetic energy. So once we find kinetic energy, we know the kinetic energy, then we can find the velocity with this equation, and we can plug that in our Python. So in Python, we've plugged everything in, like we said earlier, the angle, the gravity, the ball's mass, the t, and everything. And also we include the height. Then we find the velocity, and then we compute that out. When we run it, that's a graph of the velocity, and these are the velocity. Then we can compare the two graphs of the velocity and the height. Look at how similar they look. So the question arises, why? Why does the two graphs look so similar to each other? What's the relationship between the two? It deals with the energy principle. The height is related to the potential energy as the velocity is related to kinetic energy. So as the height increases, the potential energy increases and the velocity decreases. So kinetic energy decreases. And this is when potential energy is being converted to kinetic energy